All right, everyone. So it's gonna be the video for chapter 5. Um, we're gonna first learn how to classify um, matter in chemical compounds. So I have our textbook slides up here on chapter 5, chemical compounds. And so yeah, let's go through it. Okay, so there are three terms that you guys should know. And their differences. So we're going to classify all types of matter, right, into elements, compounds, and mixtures. Let's define it. An element is the substance that cannot be chemically converted to simpler substances. So it really is the simplest unit of a matter, of a substance. Um, you know, and if you break it down further, right, it will be no longer be that element. So if you break it down further, you start to get into subatomic particles, right? So it really is the smallest unit that you can have. And the way that you can think about an element is it has the same number of protons. So all the elements you see on your periodic table, right, they're all unique because they have a certain number of proton. Now, if that gets changed, then that means it's a different element. Okay. So therefore, all elements will have the same identical chemical characteristics. Okay, and then let's talk about a compound. A compound is now going to be more complex, right? Because element was the simplest. And you really can think about this as like Lego blocks. You guys played with Lego blocks before. So the most simplest one, like one block, would be the element. And now as you start to put blocks together to make, cool things, that starts to become what we call compound. So that contains two or more elements that are um, um, combined, uh, and it's always going to be combined in the same whole number ratio to form a compound. Yeah. So, for example, H2O, right? H2O contains two elements, H and O, and they're always combined in the same whole number ratio of 2 hydrogen to 1 oxygen, right? If it was 3 hydrogen and 1 oxygen, H3O, it would not be the water that we drink. Okay, so that's how it works. And then mixture is a sample of matter that contains two or more pure substances, and that could mean a mixture of elements of different elements, a mixture of different compounds together, like, for example, salt and water would be a mixture. Um, or it could be, a mixture of elements and compounds together, and it will always have a variable composition, right? Because you can mix things in different amounts. So for example, I could have less salty water if I have more component of water and less of salt, or I could have saltier water where I would have a greater component of, I would have, an increased component of salt, right? Compared to water. So it can have variable composition. So when you classify matter, it's basically a flow chart, right? So you can ask a couple questions. Does this piece of matter have constant composition? If it does, then we will consider that a pure substance, right? If you say no, then that means that you have a mixture. Okay. And a mixture, right, is two different compounds or two different elements. So something like coffee with cream and sugar, that's a mixture of multiple things. Now, under the umbrella of pure substance, you can break it down to two more subcategories with a question. Can it be described with a single symbol? If it can be described with a single symbol and you answer yes, then it is called an element. Okay. So there are certain elements that have um, multiple atoms, right? So hydrogen, for example, H2, um, even though it's the same hydrogen atom, it's still considered an element because it's only one type, right? One type of atom. So it's a single symbol. If you answer no to that question, then it would be a compound, right? Because here you have H and O, so you have two different atoms, two different types of atoms, two different elements, and so therefore that's the compound. Okay. Okay, so a hydrogen gas or hydrogen element is actually comprised of two hydrogen atoms. And so we call these diatomic molecules. Okay. Whereas, say, neon is composed of just an independent neon atom. So just one neon atom. It's an element as well, but we call this a monatomic element because it only needs one atom. Okay. Now, there are other elements on the periodic table that are diatomic. And let me just quickly go to the board to show you guys what those are. And you should know this. You should know the difference between diatomic and monatomic. Almost all of the elements on the periodic table are monatomic. So, when I say iron, you can just write Fe, right? When I say neon, then you can just write Ne. Or carbon is just C. If I say oxygen, you write O. Okay. So all of these are monatomic elements. But as you saw with hydrogen element, hydrogen is not just H, it's H2. So two hydrogen atoms bound together. And so that's why we call these diatomic elements. So when I say hydrogen, you should not just write H, right? Just like when I said iron, okay, you just wrote Fe because it's monatomic. But for hydrogen, you have to write H2. And what else? Oxygen also comes as diatomic. So does fluorine. So does bromine, iodine, nitrogen, and chlorine. Okay, all of these elements come in pair as a pair, right? And so you have to know that because when we get to writing equations, chemical equations, right, you have to be able to know how to write correctly these elements. So I have a cool sort of mnemonic device in which you can use to memorize this, to remember this. Hofbrinkel, right? Hofbrinkel. It's just how I remember it, how I learned, right? And it stuck with me, so it's gonna work, right? So just remember, Hofbrinkel means H2, O2, F2, Br2, I2, F2, and Cl2. Okay. All right, let's go back to our slides here. Okay, so the next picture you see is of silver atom. So silver is not part of Hofbrinkel, so silver is just Ag. Now, since Ag is a solid, right, you see that each silver atom is tightly packed together, right, in this molecular picture, right, if you were to zoom in. And that's different from, say, H2, the hydrogen element, and the neon element, because those are gases, both of those, hydrogen gas and neon gas, right? And so they're not going to be stuck together. Remember, a model of a gas, these particles are very far apart from each other with a lot of empty space in between. And so that's how that's how these pictures are represented, right? To show you that difference on the molecular level. All right, so now let's look at what a compound would look like. Okay, remember, compound means multiple, right? Elements together, at least two. If you have two different elements, then you're a compound. So water, H2O, you have a hydrogen element and also a hydrogen atom and the oxygen. So the water molecule is a liquid state, right? So in the picture, you see that they're really close to each other, but they're not orderly like in the solid state, right? In this picture here, it's showing you sodium chloride. So sodium chloride is, we call that a salt or an ionic compound, which we're going to go into more detail in a second here. But sodium chloride is made up of the sodium ion, which is positively charged, and the chloride ion, which is negatively charged. And those opposite charges attract to each other. So that's why you see them alternate here, right? You have a minus for the chloride, a plus for the yellow sodium, and they're just stacked upon each other like magnets, right? Because opposites attract. Now, things that come out of the tailpipe, right? So we just had examples of compounds. Things that come out of the tailpipe of a car, this picture is gonna represent a mixture, right? Because it's not pure. You have a bunch of different things in there. So you got water, you got carbon dioxide, you have unburned gasoline, which is octane here. And you also have, nitrogen monoxide and nitrogen dioxide. So you have a bunch of gases in there, unburned gasoline as well, as water vapor, right? So this is a mixture, okay? So that's how we classify different things, right? So just remember this flow chart, right? As you're asking those questions to be able to classify matter. Okay, so let's move on to bonding. So bonding, we're gonna go through, in this chapter, some models of bonding, like Lewis structures. So covalent bonding and ionic bonding are the main types of bonds that hold atoms together. And we're gonna see what those differences are. Okay. But the way that we can actually explain a bond is, remember the quantum theory, where we have, electron is a wave and a particle at the same time, and the wave nature of the electron is actually involved in bonding. So if you have two atoms coming together and their electron clouds basically meet in phase, meaning there's, a crest meeting a crest and a trough meeting a trough. This in phase is very conducive to bonding. You don't have to worry about it. Again, quantum mechanics is, really, beyond the scope of this class, but that's actually where it comes from. So you should know that, right? It's the in phase interference of two electron waves. Okay. So what would that look like? Well, let's say if you have two hydrogen atoms, remember that each hydrogen atom has one electron, and the electron is moving about the nucleus of the hydrogen, right? And so you see that electron cloud here, okay? And then you see another hydrogens with its one electron as well. And so that attraction between the two hydrogen atoms comes from the opposite charges being attracted to each other. So let's go back to the board and you see why that makes more sense if I draw it like this, right? So if I have hydrogen and it has one proton and one electron out here, right? So that is electron cloud. And it sees another hydrogen, which also has a proton and an electron. Then the nucleus of one hydrogen is going to be attracted to the electrons cloud of the other hydrogen and vice versa. Okay. So this is really the most fundamental reason why things bond, why atoms bond to each other. It is that electrostatic opposites attract interaction between one atom's nucleus and the other's electron cloud, right? And it's a mutual thing. So that is why atoms bond, right? And that's why these two will form hydrogen, the element H2. Okay. Okay, so this model, we call this the covalent bond because we have basically the electron clouds of two atoms kind of linking together, attracting each other, and providing a space, a region of a space where the electrons are shared between the atoms. Okay, so hydrogen will share its one electron with the other hydrogen atom, and therefore the two electrons are being shared between the two hydrogen nucleus, makes a single bond. Okay, so that's how it works. Two electrons will form a bond. And so then we don't call these atoms anymore. We call these molecules. Okay. So H2 is technically a molecule because it's not an atom anymore. Right? It's two atoms now combined together. So now when we have an H2 molecule, the electrons are being shared equally between the hydrogen atoms because the two atoms are identical. So the electron density will lie exactly in the middle of the two hydrogen atoms. And so we call this a non-polar covalent bond, where the sharing of the electrons is completely equal between the two hydrogen atoms, right? Um, so it's very egalitarian, right? The sharing is equal. Now, not all bonding is like that. Okay, so in covalent bonding, you have sharing of electrons, but they are not always equal. So we're going to see that case, right? So when it is equal, it's going to be non-polar covalent. But it is much more common to have a polar covalent bond. That's when the atoms are sharing the electron unequally, because one atom will be more dominant at taking the electron density than the other atom. And we will learn this later on as electronegativity. We'll go more in detail about that, okay? But right now, that's all you need to know is that, of course, each atom's different, and their preference for taking electrons is also different. So some atoms is going to want the electron density more, while other atoms don't care, okay? And there's a really easy general trend to remember for you guys to be able to predict which atom is going to want electrons more, okay? And it goes hand in hand with metal versus non-metals, okay? So the trend goes like this. If this is the periodic table, okay, the non-metals lie on the right, right? And remember, we said non-metals, they want to gain electrons to get to the noble gas because the noble gas has a very stable electron configuration, right? We went over that. So non-metals are going to be wanting electrons, right? So they are going to hog electrons also when they are doing covalent bonding. And so therefore, elements that are on the right side of the periodic table, which tend to be nonmetals, are more electronegative than the elements that are on the left side of the periodic table, because those are metals, right? And metals like to lose electron to get to the double gas. So metals have less electronegative. Okay. So the trend goes like this. Electronegativity will increase towards the right and up. Okay. So it's a good thing to remember to predict which atom is going to be more dominant at taking the electron density, aka electronegativity. Okay. So let's put that into practice right now. You guys get your periodic table out and identify where hydrogen and chlorine is. So now when we have hydrogen and chlorine bonding, we see that the electron density actually lies more towards the chlorine, right? Why? Because the chlorine's up here on the periodic table, right? Where the hydrogen's over here. So remember how it goes? Electronegativity increases as you go to the right. So the chlorine is going to attract electrons more, while the hydrogen attracts electrons less. And so the chlorine is going to have more electron density towards it than the hydrogen. And so we say that the chlorine is delta minus. Delta means partial. So it's not that the chlorine is negatively charged, but it is partially negative because the electron density lies more on the chlorine than it does the hydrogen. Okay. And so now what we have is a polar covalent bond because they don't share equally, right? The chlorine is clearly hogging the electron density. That's why you also see the electron cloud shifted towards the chlorine, right? And less towards the hydrogen. So the hydrogen now has a delta positive, meaning a partial plus, okay? Because it's deprived of electrons. Okay. Okay, so now let's talk about ionic bonding. In ionic bonding, you have such a difference in electronegativity between the two atoms that are interacting that sharing is not even a model anymore. Sharing is not even something that you think about anymore. It's straight up stealing, right? So it's a spectrum, really. You can see that in the polo-covalent model. One atom is more dominant and shares, unequally, right? There is sharing, but it's an unequal sharing, okay? Now, in ionic bonding, the sharing is so unequal that it's not even considered sharing anymore. It's just straight up stealing. That's what I mean, right? So you can think of ionic bonding as a complete loss and gain of electron, right? There's no sharing anymore. So which one's going to lose and which one's going to gain? Again, has to do with the electronegativity, right? And we said that the nonmetals, they like to gain because they have higher electronegativity. So it's going to be the nonmetals that take the electron while the metals lose the electron. And remember those terms? When you lose an electron, you become positively charged, and so you're a cation. When you gain an electron, you become negative because electrons are negative, right? And that term is called anion. Okay. So in sodium chloride, the quintessential example of an ionic bond, the sodium is the metal, so it will lose its one electron and it becomes sodium positive, sodium plus. And then who's going to gain it? Well, the nonmetal, right? The chlorine's going to gain that one electron and it becomes chlorine minus, okay? And we call chlorine minus chloride. That's why we name it sodium chloride. All right, so let's look at a picture of this ionic bond formation. The sodium, right, being the metal, is going to lose the electron. And how many electrons is it going to lose, guys? We've gone over this, right? What group is sodium in? Sodium is in group 1A, so it will lose one electron. Now, where's chlorine? Look on your periodic table. It's in group 7A, so it's going to want to gain one electron. So that's where it's getting its one electron from, is sodium losing it, right? And the result is that you have a sodium plus and a Cl minus. And the ionic bond is that attraction between opposite of charges, okay? So do you see how ionic bond is very different than covalent? I mean, it's still existing on the same spectrum as in, you have an attraction between positive and negative, but it's about how extreme it is, right? In polar covalent bond, you have unequal sharing. In ionic bond, it is so unequal that it's one atom, the chlorine, completely steals the electron of the sodium. We're not even talking about shifting of electron density or, unequal sharing. It's complete loss and gain of electron, right? So we're on the other extreme side of the spectrum where electrons are being completely lost and gained. And that's what ionic bonding is, okay? So what does it look like? When you have ionic bonds, we don't call these molecules because now you have an unending 3D array of plus minus just stacked on top of each other like magnets. We call this the crystal lattice. So any ionic compounds exist in a crystal lattice where you have an alternating plus charge attracted to a negative charge, to a plus charge, to a negative charge, so on and so forth, unending, right, in 3 directions, right? So you can see that in 3 directions, this is happening, okay? And this is one of the reasons why salts and ionic compounds are so stable and they're very high boiling, okay? Okay, so in summary, right, when you guys think of bonding now, you should think of it as a spectrum. And here is the spectrum, right? We start at one end where we have completely equal sharing. And this is where we say nonpolar covalent bond. And this happens when you have 2 atoms being identical, like in H2 or O2, right? Because both atoms are the same, so they're going to equally share the electrons. Or if you have atoms like carbon and hydrogen, CH bonds are also nonpolar covalent because the carbon electronegativity is not that much different from the hydrogens. So there's no like wrestling, right? There's no fights for the electron density, and so it's nonpolar covalent, okay? But now as you put 2 very different atoms, 2 atoms with very different electronegativities together, then you're gonna have one atom is gonna hog the electron density more than the other, and you can think of that atom as being partially negative, whereas the other atom is partially positive because it's deprived of electron density. And so we call this the polar covalent bond. Right? We have an unequal sharing of electrons. Okay. Then at the other end of the spectrum, well, the unequal sharing is so extreme, right? Or the difference in electronegativity is so extreme that you don't even think about sharing anymore. The model becomes one atom completely gaining the electron to become negatively charged, while the other atom loses the electron completely and becomes positively charged, and then the opposite charges attract to each other, right? Okay, so what that means is when you have covalent compounds, we call these molecular compounds because the covalent bonds form discrete molecules that that you can count. So for example, H2O forms one unit, right? One unit of water that you can hold. You can show, okay, this is one molecule of water. And then you pick up another one, you're like, this is two molecules of water. So if you can count, then these are molecular compounds. But in ionic bonding situations, you have an infinite array of plus minus plus minus. So we don't call these molecular compounds, we call these formula units. Okay, so you can see that in ionic compounds, right? There's no discrete molecule, right? You see an unending array of plus minus plus minus. However, we just write NaCl. We write the simplest repeating unit of the crystal lattice, and so that's why we represent sodium chloride as NaCl. While we should know that it's not just NaCl, it's NaCl in parentheses infinity, right? Because it's repeating over and over again, and that's how it exists. It exists as if it's glob, right? Rather than a single water molecule. Okay, so in summary, it's quite easy to figure out whether you're going to have a covalent bond or an ionic bond. Okay, so here's, a very simple, just hot tip for you guys to figure out the difference. Ionic bonding is between a metal and a non-metal. Very simple. Okay, so you just have to, that, right? Just have your periodic table out in front of you and just see what the two atoms are and whether it's ionic or covalent. So covalent bonding is between non-metal and non-metal. Okay. So let's just quickly do examples right away so you guys can see. If I say HCl, this is a non-metal, this is a non-metal. So you're going to say covalent here. CSBr. Oh, Br is a non-metal, but CS is a metal, right? So on your periodic table. So this is going to be ionic, right? You see how simple that is. What if I say MgI2? Well, this is a metal and this is a non-metal, so we have ion. Okay. What if I say CO2? That's easy too. That's a non-metal. Oxygen non-metal. So, okay, straightforward, right? I can say copper nitrate, CuNO3. So in a second, I'm going to show you what this nitrate is. It's a polyatomic, but still you can see that these are just nonmetals, and this one's a metal. So this is a metal, then a collection of nonmetal, still ionic, right? How about FeCl3? FeCl3, metal, non-metal, ionic. Okay. One more. N2O5. N is non-metal, oxygen's non-metal, so okay. Okay. Yeah, so you should know now, right? How to spot ionic versus covalent bonding. Okay. All right, so let's talk about cations and anions in a little bit more detail. We already did introduce this in previous chapter, but let's do some more. How to predict charges. You're going to go and use your group 8A, the noble gases, in order to figure out what charge things make when they do ionic bonding. So group 8A, the noble gases, is really, really stable. So what that means is everybody wants to be like the noble gas, okay? Everybody is a noble gas wannabe because it has that really stable electron configuration and everybody wants to get there, okay? So how do we determine what charge things are? Well, let's see. If you are in group 1A, okay, which makes you right here, right? The very left column of the periodic table, what is the nearest way to get to the noble gas? Left or right? Okay, just take a second. Okay, you see that if you go right, you'd have to go so far to the right, right? But if you just go one to the left, you're at the noble gas, right? That's how it works, right? You go left, you reach the noble gas, okay? So of course, in group 1A, going left means you want to lose one electron. So if you lose one electron, then you become cation, right? You become plus. And so all of group 1 metals will be 1 plus charge, okay? How about group 2? Now you're at the second column of the periodic table. Again, ask yourself, what is the quickest way to the noble gas, left or right? Well, you can see it's going to be left 2 spaces, 1, 2, right? 1, 2. So it's going to be losing 2 electrons. When you lose 2 electrons, you become 2 plus. So group 2A elements are going to be 2 plus when they do ionic bonding. Now, it even works with aluminum, okay? Look at aluminum. Aluminum is now in group 3A, okay? And what's the quickest way to get to the noble gas for aluminum? It's going to be left or right? Well, let's see. Going right is 1, 2, 3, 4, 5 spaces. Going left would be 1, 2, 3. So it's shorter to go left. So aluminum is going to want to go left 3 spaces, meaning lose 3 electrons. And so therefore, aluminum is going to be 3 plus. Okay, see how simple it is? No memorization. And this is why I keep saying, you know, your periodic table is your biggest cheat sheet. All these answers are on the periodic table. So make sure that you are using it correctly, right? So what else can you do with that? Well, you can also look at group 7. You know, you can look at the nonmetals and predict their charges as well. So if you look at group 7A, you're going to see that it is quicker to go to the right to get to the noble gases. So if you go to the right, that means you gain 1 electron. If you gain 1 electron, then you become negatively charged, right? If you're in group 6A, then you're going to go to the right 2 spaces. That's gaining 2 electrons, so you'll be 2 negative, okay? And then in group 5A, you're going to be 3 negative, right? Because you're 3 spaces from the noble gas. So you have to go 1, 2, 3 to the right. So 3 minus, okay? Look, it even works with scandium and yttrium, right? Scandium and yttrium, both, it would be quicker to go 3 spaces to the left to get to the noble gas. And so that's why they're 3 plus, okay? Now, these, the ones here, columns 1, 2, some of 5, 6, and 7A are all predictable charges, okay? And including aluminum too, right? Zinc and cadmium also, I should point out, see, zinc and cadmium is in group 12, or if you look at alternatively, it's called group 2B, and that's how I remember it, that it's 2 plus, okay, both zinc and cadmium, and they will always be 2 plus, no exception, okay? Whereas silver is in group 1B, and so it'll all be 1 plus, okay, always. So all of these, right, all of those ones with just the single charge are predictable. These ones, iron, And copper, notice, iron can be 2+ or 3+, copper can be 1+ or 2+. Actually, iron can be even more. It can be 4+, 5+, and now even 1+, new research, okay? So all of these transition metal elements in the middle are variable charge metals. And variable charge metals, they're called that because they can be many, and it's hard to predict. So we don't try and predict the transition metals, okay? We can only predict group 1A, 2A, 5, 6, 7, and then some of these other ones. Right? The ones that you can predict, I call them fixed charge metals or fixed charge ions, because you have non-metals as well, right? They're fixed because they're not gonna have any other charge. Yeah. So you should know them, right? You should know the ones that are fixed, but you don't have to memorize. Again, use your periodic table. Okay. So to name, right? To name some monatomic ions, let's go and look at these. So if you have monatomic ion, what does that mean? You just have a single atom with a charge, right? So H minus, N3 minus, P3 minus, Br minus, okay? These monatomic anions, because they're all something negative, right? So monatomic anions always get a name with an IDE ending, okay? You guys should know that. So H minus is hydride. And so how do you name it? Well, you drop the ending, right, of hydrogen. So you just keep the root of hydrogen, which is hydr, right? And then you add the suffix IDE, right? Easy. And so for the next ones, you see it's the same. Just take the root of the element name and add IDE. So nitrogen, you drop the -gen part, keep the nitr, and then just add IDE, so nitride. Phosphorus becomes phosphide, oxygen becomes oxide, sulfur becomes sulfide, selenium becomes selenide, fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, and iodine becomes iodide, right? So again, monatomic anions always end in IDE. You guys should know this. And once you know the pattern, right, you come up with others too. So other ones that are not on this list would be, let's see, what else? Carbon. Carbon's not on this list, but you can, if it was C4 minus, right, then it'll be carbide, right? Follows the same rule. Keep the root, carb, and add IDE. Let's see what else that works with. Arsenic. Arsenic would have arsenic charge would be As3 minus, right? Because look at where arsenic is. It's in group 5A. So arsenic 3 minus would be called arsenide. Okay. Yep. One more. What about Te? Te is tellurium. Spot where that is. It's in group 6A, right? And so it's gonna wanna go 2 to the right, become 2 minus. So Te2 minus, tellurium, again, drop the N and add ide, telluride. Okay, telluride is Te2 minus. Okay, so now that you know that rule, you can basically name all monatomic anions. So now you see why we called NaCl sodium chloride. We go back to the board here. I can show you. Right, so sodium chloride is ionic. Sodium is a metal, right? So it's gonna lose its 1 electron because sodium's in group 1A. And who's gonna gain it? The chlorine is in group 7A, so it's gonna take sodium's electron, become Cl minus. If you have a metal with an ion, you just keep the name of the metal, so it's easy. And then remember, to name a monatomic anion, you're gonna add the IDE ending. So that's why it's sodium chloride. Yeah. So that's kind of easy, right? Of course, this gets combined as NaCl, so we leave out the charges. But I just wanted to show you where that name comes from. And so that's why we call this sodium chloride. Okay. So now other things like this. Again, this is an ionic compound as well. You have a metal and a non-metal, right? So for the metal, you write strontium. And then Br, that's your anion, right? You know that that's your anion, so it's gonna have to be IDE ending, strontium bromide. So quite simple. Okay. One more example. Let's do MgO. Okay. So again, a metal and a non-metal, so you know it's ionic. So you know that this is going to be, the metal is something positively charged and the oxygen is something negatively charged. And we can figure that out too. Mg is in what group, guys? 2A. So Mg is going to be 2 plus. Oxygen is going to be in group, but 6A. So it will be a 2 minus. A 2 plus and a 2 minus, that's why they come together, right? To make a neutral MgO. So how do you name it? Magnesium. Right? The metal just gets the element name, and then oxygen, the O2 minus, this is oxide. Okay. Okay, here's another one. Cesium chloride, right, is Cs plus and Cl minus. Okay. Okay, and then last thing here is the polyatomic ion. So we've talked about the monatomic ions, which means monatomic means one atom, right? So Cl minus, Br minus. Polyatomic ions are going to be a collection of nonmetals held together by covalent bonds, and they have a collective charge. So they're actually more, they're usually called polyatomic anions because most of them are anions, with the exception of ammonium, which is a cation, right? And so we just call them, polyatomic ions. So NH4Cl structure, for example, NH4 is a collection of the cation. So NH4 is plus, which cancels out the Cl minus. Cl minus is the anion, right? And so you have a plus and a minus, so they come together to make a molecule, an ionic compound, cesium chloride. Other polyatomic ions that you should know, and right now, you have 2, 4, 7 right here, 7 ions that you should learn right away. These are very common, and you're going to encounter them over and over again. So right now, write a note to yourself. I need to memorize these 7. Okay. So not only should you memorize the name, you should also memorize the formula and the charge. So for example, if I say ammonium, you need to be able to say, oh, ammonium is NH4 positive. Okay. And notice what that means. It means ammonium is containing nitrogen bound to 4 hydrogen atoms, and that collective molecule carries a positive charge. Okay, that's what it means. And notice how it's formatted, right? The 4 is a subscript because it tells you how many hydrogens there are, and then the plus is a charge, so it's going to be a superscript in the upper right-hand corner. Okay, that's how you always know that that's a charge, is it's written on the upper right-hand corner. Hydroxide, that's OH minus. Again, it's polyatomic because now it contains 2 atoms, right? And it's negatively charged. So both of those atoms carry the negative charge together, okay? Carbonate is a collection of 3 oxygens and a carbon bound together with a collective charge of 2 minus, right? So again, not only do you need to know that it's CO3, but you also need to know that it's 2 negative charge for carbonate, okay? And you need to know that phosphate is PO4 3 minus. Nitrate is NO3 minus. Sulfate is SO4 2 minus. And acetate is, even a longer one, right? It contains 2 carbons, 3 hydrogens, and 2 oxygens, C2H3O2, and it's 1 minus charge. Okay, so that's it for this topic. I'll see you guys next time for some Lewis structure.